Good evening to everybody. My name is Timothy. As usual, I'm the chairman, Timar Programming Consult Nigeria. And here this night, we want to continue our lecture on machine learning coupled with deep learning with Python. So this night, I would like to introduce our tutor to you in person of Ayobami Salau. Ayobami Salau will be taking us through from where we stopped last time. Today marks the 21st of April, 22nd of April, 2024. So please, Ayobami, please take charge and let's begin the class. Thank you.
Okay, so I'll be sharing my screen now, so we can continue from where we stopped the last class. So we want to finish up what we started on machine learning. So we're going to be looking at the different machine learning algorithms actually handling. So I will share my screen now so that can can start. So I hope everyone can see my screen. Okay,
Yes, sir.
okay, good. So
Yes, we can
now,
see.
okay,
Yeah, I see it.
now let us start. So we are actually talking about machine learning. So, and everyone knows what machine learning is. And so now we want to actually see machine learning in action. So we want to build a predictive model. And we're considering the Titanic data set, and we already did some data cleaning, data preprocessing there, and we already treated and we balanced the data by actually normalizing it. So because some of the data we have in the last class were skewed, left skewed. So and we had to normalize them so that there won't be overfitting on the long run. So the model can have a very accurate model. So now what we just want to do now is we want to go into the training of the data set proper. So, and before we can fit models, there are a few more steps that are needed in order to get the data in the correct shape for modeling. So, and this involves that we split the train and test data set, followed by setting up our X train and the X test variables. So, and there's something we need to know when it comes to training data sets, creating or building predictive models. In our whole data set, we have to have what I call the training set. So for the training set, we have to have the X train and the X train and the Y train, the X test and the Y test actually. So, but in this case here, so we want to set up our training set first. So, which is the X train, which are the target. Let me the features that we want to use to train the model, so it can predict the target variable. So we can be able to predict the target variable, which is the Y itself. So note that we already have our Y train variable from before. That's when we were actually doing everything we are doing from above. So and we don't have Y test variable. So that's what we don't have. So this will be the survivor statistics per users in the test set. So that's what the test variable will be. Because if you look at the objective from the start, we said we want to see if what's the chances that someone will survive the Titanic ship sinking. So that's the interest here now, survivor. So which is going to be the Y test variable. So and that's what we are looking to predict. So we are also going to scale the data using the standard scalar tool, um, but it is not a requirement for every algorithm. So, but for those that use what is known as the Euclidean distance or the straight line distance in order to make predictions. So um, having features that all operate on different length scales will unfairly skew the model interpretation of the data. So what standard scalar does is that standard scalar aligns all features onto the same scale and thus avoid us running into issues of having to have a model that will have overfitting or underfitting. So now let us now go into the coding, the code aspect. Yeah. So now here in this case, we said we want to test set. If you look at the data set we're given data set based that which we if you look at you see that we have to train so and this is it here. We have it here. But now I want to set the target variable. Now, what is a feature and what is target variable? Like I said, the feature is the things that are needed, the point of concern that needs to be used to train the model. Target variable in itself is what we are trying to actually predict, what we are looking to predict. So, and if we look at this here, so we can set our x test to be the data set will give us from the top. So, and the x train is going to be equals to train as well. But what we did here was this. If you look at this, normally our data itself, if you look at the train itself, the train data set, yeah. So we have the X test and the X train. So we split it into two. This is just like saying we are picking a part of the overall train data set. We are picking part of it. So for the training, and also we are picking also part of it for the testing. Just like we want to pick a fraction of it. So maybe a higher fraction of this for to train, and the rest we can use it to test the model we eventually come up with. So now here, scaling the data to support the modeling. So we said we want to use a standard scalar. Yeah. So here, you said the scalar is equals to the standard scalar. So which we imported from the start. Like I said, there are some certain libraries we have to import when we want to start building machine learning algorithms, and we imported standard scalar. So, and we created a variable name to actually, so we'll be able to call it. So it'll be easier for us to call it. So, and here we now have the x train is equals to this variable now, scalar.fit, transform the x train, which is this, and x test equals to scalar.transform the x test. So now this is what we are now doing now. So the fun stuff is that we want to train our trained up data. So I'm going to tackle the modeling in a series of steps which are hopefully easy to follow. And it is just in four phases. Now, what we want to do is just this. We want to train the initial models, and after that, we will remove features and retrain. And there's a reason for removing features and retraining. Now, although we might want to use all the old features to train the model, now there is always a shortcoming to that. Now the shortcoming to that is this is that there are some there are some features that will not allow the accuracy of the model to come up a bit higher. So we will investigate that, and on the long run, we'll remove the feature that is not contributing to the model performance. So that's why we are going to remove some features and retrain. So now after we have removed some features and we have now retrained, there's something we are going to do. We're going to tune the parameters. So now after we tune the parameter and we still see that the accuracy is not still giving us what we want, so we'll still what we'll still retrain again after tuning the parameters. So that's for removing the features and retraining, then we tune parameter and retrain. So the fourth step is we are going to build into a voting classifier, and we are going to predict. So I will tell us what this is in a bit. So now all these steps we are going to explain them as we flow. So now the round one. Now the initial models. Now when we say initial models, that means we are talking about some models. So now the current problem is a classification problem. Yes, you can say it's a classification problem because why do we say it's a classification problem? It is because we want to predict survival. So did this person survive or this person did not survive? So and that is the outcome. That is the outcome can be classified into one class or the other, which is survive or not. So each of the below algorithms is applicable for such a problem, and I am interested to see how each of them perform on the current data set. So we want to see them and which comes out on the top. What we are talking about is predictive modeling that is using machine learning that is selecting the best fit based on data pattern. So which means that what we are interested in is that we want to, okay, on the longer run, want to make sure that whatever model that comes up at the top is what we are going to actually choose. So and say, okay, this one is the best for the work. So now I would encourage to check the scikit-learn documentation for more detailed overview in regards to how each algorithm specifically works. So, and if you look at the official documentation for the scikit-learn, are going to see are going to see the different machine learning algorithms and how their use cases, how they are being used, and examples of data sets that are code alongside. So now, what I'm going to do here is that we'll fit each of these 11 models in turn. So now we are considering 11 models now. So which I talked about. So and I gave us we saw how we imported all those algorithms from the top. So now before returning what is known as their cross-validated score. So a model performance is dependent on the way the data has been split. I will say that again. The model's performance is dependent on the way the data has been split between training and test data. So the way we split our data, the performance of the model will actually depend on that. Now, for example, if I split my data into 80% to train, 20% to test. There's something, and if you look at 50% to train, 50% to test. Now, one thing about model, and we want your model to perform very well, apart from we are done with feature engineering and we have normalized the data and we have a balanced data set. Now, something we must put into mind is that the higher the data set and the better the model. Like the if I say, okay, for example, now, if I want to build a model that predicts loan prediction, if for in university setting, for example, ASU, so that is in federal universities and state universities that have ASU cooperative. So now, how can we build a loan prediction model based on the loan that you have taken before your the duration you used to pay the loan and some other scores like that, some other features. So how can we know that okay you are eligible for another loan, or you're not eligible for another loan, maybe you have to wait for some months or for some weeks. It's based on the fact that if you have more data set, the more the data set, and the more the features, and then the better the model performance and the splitting of the data. So we need more data to train the model. So in order to get a higher performance. So now, but this isn't really that representative of the model's ability to generalize, because there could be unique quirks within the train or test set which the model either learns or does not learn incorrectly. So which means that whether the model itself was able to learn what it was able to learn in the data set. So due to maybe inconsistent data, or maybe the data is not, let me say, maybe the data is, let's say, not actually credible. So, but in order to gain a smooth out representation of the full data set, there's something they call k-fold cross validation can be applied. So it works in the following way. So now this is what k-fold cross validation does. So we randomly split our entire data set into k-folds. So now this is it. Now for each k-folds in our data set, we build our model on the k1 folds of the data set. Then we test the model to check the effectiveness for the kth fold. So, and also we record the error we see on each of the prediction. So then we repeat this until the k folds are served as the test set. Now, I will still come back to this. So, because it was explained in the material itself, that is the PDF sent to us. So, the average of our K recorded errors is called the cross validation error, and it will serve as our performance metric for the model. So, and we are going to use 10 folds in this example, so which will be plenty. So, we'll still get back to that. But now let's go into the main thing, the business of the day. So now we want to initiate the 11 classifier models. Now, here now the random forest classifier. We have the random forest classifier that we imported from the beginning of our notebook at the very top, remember. And the KNN, the logistic regression, the SG boost classifier, the gradient boosting classifier, support vector, extra tree, other boost, Gaussian, and Gaussian boost classifier, bagging classifier. So now we created a variable, which is this. So it will be easier to call them. So that's the essence of using this. And it's not necessarily, it has to be this exact name. You can put anything you want to put, but make sure that for easy notification, that's to notify them easily or to remember them. So you put something that is actually correlating. So like this one, gradient boosting classifier, GBC. So it's very easy to know that it's gradient boosting classifier. SVC, support vector classifier. So it's actually easy. So that's the essence of this. So now we now put the um, all the models itself. Now the algorithms, we put them in a list. So, and what's the essence of putting them in a list? There's a reason for that. So we put them in a list so that we can have access to them easily. So now, sequentially fitting and cross validating all the models. So now we create a for loop here now. So now the for loop is this. We said for mode in models. So that's mode dot fit. So now X train, Y train. So here now, we now said the accuracy should be equal to cross underscore validation underscore score. So where the mode itself is going to work on the X train, the Y train, then the scoring is accuracy. So which the cross validation is going to be equal to 10, like we said. So that's the K fold we want to use. So say we are using 10. So then scores dot append So the accuracy, so now the is the mean that we want, the mean of the accuracy. So now the above for loop, because this is a for loop, the above for loop, what it does is that it has packed the level models, it has packed my level model cross validated scores into the list score. So now I am now going to unpack this data into a table first, then graph to learn the result. So what we are trying to do is that after we actually use the algorithms on the data, then we are going to be able to graphically see or view the, the score, yes, to see which algorithm performs better. So, but note at this time that our scoring metric is called what? Accuracy. So, and this is the competition requirement, and is simply a percentage count of the correct classifications provided. So now for classification problems, however, it is not always best practice to use accuracy. Listen again. So for classification problem, it is not always best practice to use accuracy as your scoring metric, but consider a data set where 80% of the target is class A and the remaining 20% is class B. So an accuracy score of 80% on this data set might on face value sound positive. However, the classifier could have simply predicted every observation as class A. So there are 80% in class A in total. Thus, it is 80% correct. So this model clearly lacks any real use, but a misleading accuracy score could prevent that being so easily spotted. So metrics such as precision and recall, or the uh, receiver operator curve score, can be used as an alternative scoring metric for classification problems. So this is very important. You need to take note. So this using accuracy score alone is not okay, is not good enough. So, but there is a reason why we said you should use this. Now, the reason why we say you should use this is because, for example, if we have an imbalanced data set, for example, here now, this is talking about an imbalanced data set where we have 80% is class A and 20% is class B. So that alone will actually cause model biasness. So which will not actually, and if the accuracy score is 90% or something, so we think maybe it can actually the model will work fine. No. So the best way to actually see if the model is actually okay is to use precision and recall score, then receiver operator curve, and so on and so forth, like that. So that's the best way. So now we want to now go into the main thing now. So what we want to do here is this: is that we want to uh, do the needful. So what we want to do here is we want to create a table of results that so it can rank the highest to the lowest. That is based on performance of each algorithm. So now what we did here was we said result is equals to, you should return it as a data frame that's in form of a table, which is something of this nature. So now we now said model itself. So we now pick the model random forest. We have the k-nearest neighbor, logistic regression, so XGBoost. We listed everything that the models we considered for the classification problem. So then we now said that it should also return the scores. So now we just created a random um, string. This is just a string. So normally, so this is a string. So now what we now say you should do is that the data frame should be returned in this format where we have model, which is this, and we have score, which is this as well. So, but what you should return, so this all these algorithm. So, in the order of the way you should sort it is the higher the score, then the higher the preference it's given to appear at the top of the table that we said the data frame. So, we now said the result of the data frame is equals to result dot sort values. And how should the sorting be? Should be sorted by the score. So which is the accuracy score. So and the ascending, we said ascending should be first. What we mean by ascending should be first means that is that it should not be in increasing order, but it should be in descending order. How do we say ascending should be true? Then it should be going in a order where it moves from lowest to the highest. So in this case, it's going to be from the top to the to the bottom. So which we can see here. So and we said it should return the data frame of the so called accuracy, the score, yes, accuracy score the for the models that we are actually considering. And mind you, we already trained the model here. Actually, we already did that in this place here, and this is due to the fact that we are using 11 algorithms here. So now we just wanted to see the accuracy for all those models in a tabular form. And mainly looking at this, we can see that the support vector classifier took the first position, the gradient boosting second, logistic regression the third. So which we can see. But now also, if we want to see this tabular um, scores, we want to see it in graphically. So this is it. So we can see graphically here, whereby the plot result, we have it here. So we are using Seaborn. We created a bar plot here from SNS. So SNS.bar plot. So the x axis should be score, so which we can vividly see here. And where we also say the label should be called accuracy score, which we are seeing here. So which we have here outrightly. Then we said y should be the model. And what is the model? The model, which is this here, which we have here. So and which we said the y label, gave it the label should be algorithm, which we have here. So, and we also set the limits of the x axis, the scale. So the scale should be from 0.80 to 0.86. And why did we do that? Is because we can see the comparison vividly. Because if you look at it, we can see that the accuracies for the 11 algorithms ranges from 0.80 to 0.86. So which it will be more clearer if we are comparing. So which we can see just this way. So that's why we can see that our x-axis is running from 0.8 to 0.6, 0.86, okay, which we can see here. So now the same result we have in this table is the same thing we have visually here. So there's no difference from what is here to this. So we are just trying to the graphical representation makes us have an idea of what we are looking at. So which we are saying that the Gaussian naive Bayes did not perform very well, although the accuracy score is high, yes. So but it's not compared to the support vector classifier and gradient boosting. So now the round one is complete. Now, the round one that we said we want to train the initial models. So which we just did, and we can see the accuracy and which we have accurately seen. So now the next thing now is that as the round one completes, and it is the gradient boosting algorithm that comes out top. This isn't a surprise because gradient boosting is a machine learning technique for regression and classification problem. So we need to take note of. So a gradient boosting algorithm is a machine learning technique for regression and classification problem. So which produces a prediction in the form of an example of weak prediction models. So which is typically like a decision tree. So it builds the model in a stage-wise fashion like other boosting methods do, and it generalizes them by allowing optimization of an arbitrary differentiable loss function. So and they are typically regarded as best in class predictors, and they form the basis in many winning competition models. So which means that actually basically due to the we can admin we can go to the we check the official documentation of that scikit-learn, and we look at the gradient boosting. We can see so gradient boosting actually is one of the choices that actually for classification problem and regression problems, so which we are considering. So, and I want to now see how heavily each feature was linked in the modeling process. So now we want to see the feature. We use some feature to train. So the features like the P class, the arc, arch feature. We have the designation, which is the Mr., Miss, Mrs. So all those features, we want to see how heavily each feature contributed to the SG boost. So let's look at what feature SG boost found most useful when it achieved the top score in round one. So now to help present this data, I'm going to construct a graph of my own, and the graph which you are going to actually see, which is something of this nature. So what we want to do is just this: we want to see the feature. One thing there is this is that the algorithm itself, what machine learning is all about is that we feed it with the features we want it to we want to use it to train the model. And after feeding it with the feature, it now digests the features and learns everything that has to do with the features, learns the pattern, hidden insight, and it comes up with a model, and the model is the pattern it has learned so that you can use it on the long run to make predictions on unseen data. So that's just the essence of what we want to do just now. So we want to see which feature. So now the function that we want to create now, we want to build another function. So we said the function for the new graph is uh, we define a function which is called importance plotting. So which we picked our data, so which is the data we imported from the very beginning. So we set the x and y axis, and the palette we picked palette the title. So we said that we use Seaborn. We set the
Okay,
style to be white
now.
grid.
Hello, hello.
Hello, sir.
I can see you are now at cell view 3, right?
We have here is that I said that I created a function for a new graph, and the graph, the essence of the graph is that we want to actually be able to view the feature that the each algorithm find very useful during its training process when it was feeding on the data, on the features itself. So which one does it find much more important? So and this I said is very, very important when you are building predictive models, because well, most of the time the way we do it, we build models and we don't actually take cognizance of that. We just only okay because I build the model, the score is higher. You know, there's no need to do further analysis to see which feature the the algorithm find very useful. So if we can know which feature the algorithm find very useful, I think that will help us on the longer run to be able to go back and do maybe um, data normalization again, or maybe some feature engineering, further feature engineering on that particular feature to go and check if the feature still needs to be normalized, or if the feature is left skewed or right skewed, so we can actually concentrate on those features that are very important. I hope I'm communicating a point. So if we can actually get to know that, then we can actually say, okay, since this feature is the most important thing, then okay, I think we need to focus more on the feature, and so that we can have a higher and better accuracy, so that the model can perform very well. So now this function that we are seeing here now is importance plotting function. So what it does is that It's going to allow us to be able to see the importance of each feature as relating to the algorithm that is being used. So now, building the feature importance into a data frame. So now, feature importance, which is F5. So we said the feature, which is just this is a dictionary here. It's a dictionary. So we have feature, which is string dot columns dot return it to a list, and the importance as sgboost dot feature importance. So which feature is very important to the sgboost. So then we now said the importance is equals to PD dot data frame, feature importance, the index, should not put an index, you should sort the value in such a way that we have importance in ascending order. So we can actually view this importance. So we want to view it, you can. So, but here we want to now say, okay, creating the graph title. So the title, what title do you want to give it? I want to say the most important features in predicting survival on the Titanic. Yeah, for the SG boost, the most important features in predicting survival on the Titanic. Just like saying the most important feature that we can use to actually know or to predict loan prediction or to predict customer churn or to predict if um, a customer will come back to buy a product or not. So this is just the way the title is. So now we want to plot the graph. So we now plot it this way, where we have the importance, which is we have the importance here. We look at this. Remember, we have it as these titles. You remember, if you recall, this is the way we said you should plot it. So we call the data, then the x-axis, the y-axis, the palette, and the title, which is just exactly what we have here. So we are calling the function because we already, the function, this is the function that plots our graph. So we are just calling it to invoke the function. So it does the plotting. So, and this is it. So this is what it gave us. And looking at this, if we look at this for the SG boost, which feature is very, very, very important? So mainly looking at this, we can see it's the title. The title is what we find very important. Then followed by family survivor, then the P class, so the cabin, then it keeps going down. So it finds the sex not very useful, so to say. So now, always the most interesting, in my opinion, way, the imputed age feature went down a trait with SGBoost, which means it's not useful, just like it's useless. Very, very useless. So now followed closely by the new family survivor feature. Yeah, family survivor. You know, we created this new feature when we were doing feature engineering. Yeah. So, and I'm pretty happy with that. So now we have sex, cabin, and embarked were a little more well useless. So, which we are seeing. So, score solo indicate that these features more likely hindered rather than helped in the model prediction. I say again, these features that we are seeing here, you can see this. It rather did what? It rather hindered the model prediction than helping. So now let's now check out a different top performing algorithm. So now we can see that in this feature. So now if you now want to train the model again, basically because of this, we can now retrain this model using SGBoost, and we can just remove these two and say we don't need these two. So if you see, if you remove these two and retrain the model based on the rest of the features that we have here, then the accuracy that we have for the SGBoost, that is um or the SG boost, which is this, yeah. So the gradient boosting, which is we can see there, is going to move a bit higher. So it's going to move higher. So now we want to check for different performing algorithms uh, outrightly again. So we want to pick others. So now what we want to do now here is this, is that we want to also check for logistic regression. So we pick the feature, so we pick the logistic regression in this case, and we also look at, for the logistic regression, which features contributed more, or which feature did the logistic regression actually find more useful. So we can see here title, family survivor, and sex. So this is not something that is very intriguing. We know normally when it comes to logistic regression, it will actually find sex very useful, yes, as a feature for logistic regression, which is the most in most of the case, yes. So we can see it here. So we can see family size and P class and age. They are my negative values or in importance. You can see them. Yeah, negative values. Even embarked is even very low, yeah. So, but merely looking at from cabin up to title, I see that they have very high importance. So now, rather than the feature importance, logistic regression uses coefficient, which actually aid better real world interpretation. Which, like I said, so they are both positive and negative impact features on display. This time with title being the most useful, and sex is also a strong feature for this model. So in stark contrast to SG Boost, those in the middle, which is embarked, fair, and the cabin, also all had largely no part to play except for possibly creating unhelpful noise in the data set. So, and as we know, noise weakens the model's ability to find patterns clearly and can, in some cases, lead to lower overall performance. So, and embarked and cabin are two repeat offenders. That is in the SG boost that we compared at the top here, so which we can see here, so which they are noise in the certain case. In the same case here for the logistic regression, we can see that they also did the same thing again. So which means that this feature, which is embarked fair cabin, in short, this family size, P class, and age, they are useless, so useless. And now, they are creating noise. So, what do we mean by noise? Noise means that the ability for the model to find the patterns clearly in the data set, the insight that it needs to gather. And mind you, some of us are fond of something because we have data and we see numbers and we want to be, all we just do is this. Okay, this is what I want to predict. Okay, this is my target variable. These are my features. As far as I'm seeing numbers, or I can encode and turn them into a number. Then I just pack everything, put it inside the algorithm. So we start training. That's just it. So we don't want to know, okay, on the longer run, which feature is actually contributing more and which one is not contributing more. So which one should I remove? Which one should I not remove? So I would beckon on us to factor this scenario into any work we are doing when it comes to building a predictive model. So which we can actually filter and know which feature is actually useful in the algorithm. So now, round two. Now, you see, there's something I want to let us see here, is that what we did initially was to train the models, and not only just that, we actually look at SG boost. We say it's good for regression and classification problem, and we look at logistic regression as well. So, which is very good in the case of a classification problem for this Titanic data set. We want to predict survivor, so if survived or not survived. So now we did that. We saw the score. Yes, we saw the score, and after the score, now we now looked at the importance of the feature, how important the feature is. Well, in terms of each algorithm we use, we considered XGBoost and logistic regression, and we saw that there are some features that are not useful. There are some that are useless. So we saw that, and which is very very clear, and which we can see. So now, what we now want to do is this: is that after we did this, what we want to do again is that we want to now do feature selection. Now, so we want to look at the model and have a few particularly strong performing models. However, where are we failing to harness the true potential of each model data set due to the features that are creating noise? The following steps we walk through how we can optimize our baseline prediction to yield a stronger overall score. So now the first step is feature selection, and by that I mean carry forward helpful features and remove contributing towards the model performance. So this step I anticipate should help to unshackle some currently weak performing models. So now, why some models will not perform in reality is because of noise. Yes, some features that are not contributing. So if we remove that, we can see, or maybe we'll be able to see if some models will perform better. So now we are looking at the k nearest neighbor model. When I say this, so the k nearest neighbor should be able to move up the rank because it's also good for a classification problem. So now to get a better gist in terms of what needs the boost. So we are going to get a collective view of all the models that will give us a feature importance list. We can then compare these values and draw a cutoff for the features that overall provides the least amount of help. So what we are trying to say is this is that we want to see which one is going to actually the feature we need to delete or erase totally. That's what I'm trying to say. So, and by so saying, so we are trying to look at gradient boosting classifier, SG boost. We have RAN, we have other boost, and we have this as well. So we just want to look at all this. These are the ones we are considering. These five models, and we want to match the result into a single data frame. Yes, yeah. So, and merging the results, we want to calculate the average importance per feature and also rank from top to the bottom and display it. So now, after doing all of this, and what we did, we have here was this. So now we saw the importance in terms of the feature when it comes to all the five algorithms. We want to look at the feature that is performing very well. So, and we rank it. So looking at this, yeah, the league table is out and we have a winner in which is title. So maybe this isn't so surprising given within title information on both age and gender is available. I find it interesting to see that where some models lean very heavily on a certain feature, others gain barely any value from it. So the age striking. So let's get this data into a final graph before making a decision on which to call. So looking at this, um, comparing the for the gradient boost classifier, if you look at this for the importance, you can see that the impact is so low, and also it's the same thing here and sex as well. So and we can see that the impact is just repeatedly giving a poor score, important score, and the same thing as sex and age. But although in some certain cases, some algorithm find it very useful if we look at it, but looking at it here, we can't see it very well. So we want to all we want to do is this is we want to do something. Yeah. So we want to combine these five algorithms. Yeah. So we took the average. So the average for the title for all the five algorithms is this. This is the average, and for survival, this is it. As family survival, P class, we have this family size. So in order of descending order. So we have it here. So which shows that title still comes up at the top. So now after now combining the most important feature in predicting survival on the Titanic for the five model average, we still see that what we find very useful is the title. The title, very important, family survivor, passenger class, family side. So this is the graphical uh, appearance of this, which for the average. of audio feature that we are considering. So now it looks clear now that embarked and cabin really aren't helping us out, and therefore we are going to get rid of them. And if was looking to prioritize one or two model rather than 11, so we would have also considered removal of sex. So, and remove sex, fair, and potentially P class too. So, but depending on which were the models I was considering, so we would have done that. But what we are removing first is embark and cabin. So they are useless. They are not useful. However, we can see from the above table that for some algorithms, each feature has an important part to play. And I want to prioritize strong performance across the board in preparing for the voting classifier. So we'll talk about that later. So for now, it's just the two for the chop. So which means we are dropping redundant feature, we are dropping embarked, and we are dropping cabin. So they are not useful. So and we want to rebuild a model variable. So we rebuild it. That's xtrain xtest. So and we'll also transform it. And now we will now come ahead with the model retraining, because why do we want to retrain? We dropped two features. So and we hopefully we'll see some increments in the accuracy. So we called the algorithms again, then we did the same thing again, just as we did at the top, and we also matched the original score as before, and the score with feature selection after dropping embarked and cabin. So this was what we got again. So we now want to compare. Now, I think we were able to see a considerable amount of growth. Can we see that? So if we compare this, you can see there's an increment. Yes, there's an increment, there's an increment. So across board for everything. So which means that um, the cabin and the embarked, there was noise for the accuracy not to come very high. So by removing those two things, so the accuracy will get more accuracy. Yes. So now, so plotting the result for the new score with feature selection. So we can see this here that we have this here. So just some great stuff. So some big shifters on display. So Gaussian process now leads the pack. So Gaussian process here, you can see it. And initially, Gaussian process was not leading in the initially. Gaussian process was not leading initially, because Gaussian process, if you look at it, the position for Gaussian process here was this. Now it is now leading due to the fact that we dropped some features, just two. So you can see Gaussian process is at the top now, which we can see is leading. So now this is all we want to do. Okay. Um, the KNN model is now also mixing it up at the top, so which you can see here, KNN. So it's coming up as well. So and Keras prior to feature selection, it was languishing down at the bottom in all, which is position 9, K9 is in the ball. So models have improved in score with XGBoost remaining static and other boost taking a slight knock. So other boost came down a bit. So and which came down, and this is okay. That's a very favorable from something as simple as removing two features. So we can now progress to round three, which is model tuning. We want to tune the model now. So we just did some things now. So you can tune the model. So model tuning, which is hyperparameter. So which, if you remember in the material itself, we discussed hyperparameter extensively. So which was the theoretical aspect. So now, within most machine learning algorithm exists a number of parameters that together can be fine-tuned to produce the most accurate prediction on a given data set. So this is essentially what hyperparameter tuning is. So finding the best parameters for your model that we want to build. So the best way to achieve this, while computationally expensive is to use what I call grid search CV. So grid search CV is an exhaustive search over specified parameters value for an estimator in order to find the value for optimum model performance. So each model has its own parameters. So the grid search needs to be specific for each model. So below, we'll complete a grid search CV for each model that we are using, for each algorithm. So specifying search ranges for each model's most important parameters. So in order to find the ones that yield the highest accuracy score for the Titanic train set. So for your information, if you are okay, let us leave this. So let us now take this. Okay. Now let's go into it. SVC. Now, for the SVC, we want to do search, grid search CV. So we have parameters to search. So we said the C's should be 0.01 down to 100. So, and the gammas should be this. So now we want to set up the parameter grid using the C's and the gamma. So we created a dictionary, which is this. So now we now run the grid search CV. So we said that the estimator should be SVC, that's for the support vector classifier. So where we use the above parameters, so and give us the scoring as accuracy, variables true. So now we now print all the things, the score and the estimator, best estimator. So we saw that fitting five folds for each of 40 candidates, totaling 200 feet, and 0. We have a score of 0.85744, 146, and so on. So the support vector classifier uses a series of 1 and gamma of 0.1, and the probability is true. So which from here, it uses a series of 1 and a gamma of 0.1. So we are still going to come back to all this. So now we also check for the gradient boosting classifier as well. So the learning rate, parameter to search, the learning rate, the number of estimators to use. So the upper parameter to search for. So we now run the grid search CV. So we get that fitting five folds for each of 56 candidates, totaling 280 feet. So this is the score. And the gradient boosting classifier, the learning rate, what it gives that it uses this, and the number of estimator is 1,250. So now, same thing for logistic regression, we did that. So used penalty, so L1, L2. So we use C and we created the set of the parameter grid and we run it. And we have this accuracy and we have the C scored to be 2.782. So fitting five folds for each of 20 candidates, totally 100 feet. So for the SG boost, so we did this. It gave us this actually. So, but we also carry out another step because for the step one we got this, and for step two we also got this. So, but the accuracies are different. Yeah. So, and for the step three, we had to do something here in order to make sure that we have we still have this accuracy score here. So which is fitting 5 foot for each of the five candidates, totaling 25 feet. So we have step four, so which is this as well. So we keep on going for that, and we have accuracy which is this is 0.85518. So which are five steps that we used for that is the SG boost. So and one thing there is this is that the gradient boosting algorithms are best tuned sequentially. So that's why. So it is less expensive and can yield better results. So and which was demonstrated below. So, but it is a slower algorithm to run, and I'm obviously too impatient. So that each time I find the appropriate parameter value, I will specify this within my model in the subsequent test step. So it will take time. So that's why we are just doing it sequentially. That's why we took us 5 steps. So for the Gaussian process, we also did this as well. So we have this accuracy. That's for the grid search CV for the parameter tuning. For the other boost, we did the same thing as well. For the k nearest neighbor, we, we we chose number of neighbors from 1 to 20. So algorithm should be automatic with the weight uniform distance. So we did this and we set up the parameter grid and we run the grid search CV and we had this fitting 5 folds for each of 300 candidates, totally 1,500 feet with this accuracy. So the leaf size is 25 and the number of neighbors is 20. So for the random forest as well, we chose number of estimators. So that we want. So the depth, the feature, maximum features, minimum sample split, minimum sample leaf. So we come up having fitting 5 folds for each of 1,000 candidates totaling 5,000 feet. So we have 0.8585 as the score, and the random forest classifier has maximum features 5, minimum sample leaf of 4, number of estimator 10, and minimum sample split 6. So for the extract phase, we have this as well. The bagging classifier goes on the so now the Gaussian A base doesn't have parameters to tune. So we are stuck with the current score. So it doesn't have anything to tune. So for the Gaussian A base, you should take note. So this algorithm is known to be designed to work best on text data. Example, once passed into a matrix. So perhaps in comparison to the other algorithm, it is less of a surprise to see it performing less favorably on the Titanic data set. So we can't do parameter tuning here. So we just hold on with this course. So now after we have done all those parameter tuning now, so we want to now retrain the model. Now, so we are into the round 3 now, and hopefully optimizing more of our models and really squeezing every last drop of predictive out of the data set. So we'll run the same procedure as before and stack the latest results against the 2 previous one. So the only change now is that we have to specify exact parameters as per the above grid search results to yield even better performance score. So all the grid search CV results, we now stack them up here. We put them up for all the 11 algorithms. So except for the Gaussian um, naive Bayes, as we see. So now we now created a table for the results to from the highest to the lowest, just like we did earlier on. So and we merge it so we can see the score with the tune parameter. So now did any increment occur? So looking at this, yeah, we have comparing this and this, we have the same score. So we also have the same score for the support vector classifier. And then for the gradient boosting, the score actually dropped. So the score increased for random forest, the score increased for extra trees, score decreased for KNRS neighbor, score increased for other boost, for logistic regression, score is the same. For the SG boost, score dropped. For bagging classifier, we have the same score. So the Gaussian A base is still the same thing. So we carry that over because it doesn't have parameters in it. So which we see. So now plotting it visually, we have this. Yeah, just as we can see here. So I hope we are following what I'm doing. So I want a response, please. It won't be like I'm just talking and talking.
Very well, very well, very well, very well.
Okay.
Well done, sir.
Yes, sir. So
Yes, we are good, sir.
so now for the
You
round
want you want us to say something?
No, no, I just want to know if you are following. So
Yeah,
because
we are here. We are not dead.
the class is quiet,
We are
too quiet.
following. It's very, we are good, sir.
Okay,
You
so
ask
we'll
more
continue.
questions when you are done with the machine learning.
Okay, so now we want to now round up the round three results. So round three results in, and the Gaussian process remains our strongest model. So I actually omitted parameters for a few models where I saw the score had dropped subsequent to specifying them. So I presume this could be because I did not test the full set of parameters in those cases. So the Gaussian process score remains as before, but for the extra trace classifier, it has shot right up into second place after a 2% jump in accuracy. So there's a 2% jump in accuracy. So for the um, that's for the support vector. That's sorry for the support vector. So now, aside from the Gaussian naive Bayes, each model now predicts over 84% accuracy, which makes sense. So a strong set of final models which I can now carry forward into the final step. So now we want to do a voting classifier, but mind you, now other than the voting classifier, now we will come back to that actually. So looking at this now, out of the 11 algorithms, which one should we go with what we have seen here now? After we did what the now we also now did feature importance to know which feature is important, so to know which one to drop, and we dropped them. Some models, the accuracy skyrocketed, some dropped, and we also did hyperparameter tuning. So, and with that, we were able to see that Gaussian process remains our strongest model. So now this means, in one word, Gaussian process is the best algorithm, that is the model to choose for this case, for this data set. So when we want to go by selecting best fit based on data pattern, yes. So which one are we going with? We're going with the Gaussian process. Although we can go with the random forest or gradient boosting or support vector classifier, but we can go with the Gaussian process because of the accuracy and the performance of the model itself, the algorithm itself. So we can choose the Gaussian process. So before we move, okay, I want to, before I move into voting classifier, there's something I want to talk about before I move there. So now, whenever we are trying to build a machine learning model, so to say, so there are some things we need to always consider. Like I said, like I said, I said feature engineering is very, very important. Very important. So now, because of our feature engineering, we were able to eliminate the feature that is not needed, even while we were training the model and to see which feature were important. So now, our strength should lie in the data preprocessing. So, whereby we first of all we clean the data, we balance the missing values, then we normalize the features that are skewed, and then as well we do feature engineering. If we can combine some features together to get a better feature that can help in our model, then we should do that. If it is to drop a feature, we should do that as well. So feature engineering is very, very important when building a machine learning model. So, and also, I want us to take note of something. So, um, when we want to build machine learning model, so I'm not saying it's but we should take this type of approach. So if we are dealing with, let me say, for example, we are dealing with classification problem, then we should try as much as possible to go with classification algorithms as much as possible, and can choose which one actually is going to come out at the top for that particular data set. So you can choose the one that will have the a better performance. So that's that about that. So now voting classifier. Now, why are we using voting classifier? So I'll talk about that. Now, voting is one of the most simplest ways of combining the predictions from multiple machine learning algorithms. So now, why did I turn to this side? Although we were focusing on looking at singular algorithm that performs better, that comes at the top. Yes, we have achieved that. So this is just more or less like an addition. So voting classifier means we have, I don't know if I don't know if you have heard about what they call super learner. I don't know. That word super learner is just a way they are because nowadays, because of the ability of some algorithms not to give a better accuracy of prediction. So some machine learning experts try as much as possible to merge many machine learning algorithms together to get a higher result, a better result. So, and this part of it is just this voting a classifier. So now it works by first creating two or more standalone models from your training data set. A voting classifier can then be used to wrap your models and average the predictions of the submodels when asked to make predictions for new data. So that's just the way the voting classifier works. So a voting classifier can be used to wrap around your models. That is, you can create two or more standalone models. Then we can now wrap the models and average the predictions of the submodels, which that are standalone when asked to make predictions for the new data. So there are two types of voting classifier. We have the hard one and we have the soft one. So uh, now the thing there is this is that okay, don't let me go into this. I don't want to go into this Q&A stuff so that it won't bug us. So, but I want us this. I'll give this as a discussion on the group. So this I want this to be a discussion on the group. So, or let me just continue. So this will be a discussion on the group. So now let us just go into what the voting classifier is. So we won't waste much of our time. So now the code below completes both a hard and soft voting classifier on 11 models. So minus the Gaussian naive Bayes, which due to its poorer score, we will omit from this final step. So, and we will then compare the scores of either classifier before selecting the best to proceed with making final predictions. So now add vote or majority rules. So tuned hyperparameters. So what we did here is we said grid search is equals to, we use the voting classifier library that we imported function itself. So we now say the estimator should be random forest, which if you remember, this we already declared above as the boost, gradient boosting classifier. So and we now said grid add CV is equals to model underscore selection or cross validate grid add. So which is this. So on the X train and the Y train, so cross validation 10, return train score true. So grid add dot fit, so you should fit it, then print add voting on train set score, it should be the mean. So then print add voting on test set score as well. So now add voting on train set score. The mean score is this 86.15, and the add voting on test set score is 85. So which actually makes sense at least. So that's for the add um, voting classifier. So now for the grid the soft one, so we did the same thing. So we just used the grid soft. So now it gave even a higher accuracy. So 86.96 for the on the train and 85.97 for the test. So now it is it was pretty close, but for the test set, the soft voting classifier came out just on top. So we'll proceed to use this as the final model for prediction. So we'll complete that final step below before wrapping up. So before we wrap up, so now this is what we want to do. So the final model prediction is this is prediction. So the predictions is going to be equal to grid soft.predict on the X test. Then so now we have submission pd.cocat pd.dataframe passenger id. So then pd.dataframe predictions. So submission of columns. So passenger id then survived and submission dot to csv titanic submission dot csv. So now this is just go. So in this kind, I've taken several steps to and I'm fine-tuning the selection of classification models for a final test score of 86%. So which we use that is for the voting classifier. So which means that we combine the 11 algorithms together and take the average of it and use it. So anytime we want to actually make prediction on new data sets, then it uses the voting classifier. So now I've hopefully been clear with my code and sufficient in my explanation so that you have been able to read along and enjoy the ride with me. So I do intend to return to this channel to add in more information where I can do and because okay, well let me just bother us. So now another thing we can do here is on your own you can explore new features in the data using a predictive model to impute age rather than a single group by operation or investing more time in parameter tuning and model optimization or prioritizing fewer models and thus cutting more redundant features or exploring deep learning application. Another is to use deep learning. So, but now that's even not the case. The case now is this. We want to, we talked about that we don't like using accuracy score. So we want to use the ROC curve. So the ROC curve, precision and all those scores like that. So the confusion matrix and so on and so forth. So we have the receiver operator curve using cross validation. So this is what we have for the area under the curve. So we can see this. And we have the precision recall curve using cross validation as well. So we can see it. This is just it for the precision, then for the recall. So and we have the confusion matrix. Now, if we go back to comment, please, we go back to the that's all right here.
We have less than 5 minutes for this class to end.
Okay. So if we look at this okay, for the receiver curve. So we said receiver operating characteristics curve that plots the true positive rate on the y-axis and the false positive at the various on the x-axis at various threshold setting. So now the TPR is also known and the FPR is one minus the specificity. So now the area under the curve is indicated as 0.89. So, which is a measure of the model's ability to discriminate between the positive and negative classes. So, and AUC of 1.0 represents a perfect model, while an AUC of 0.5 represents a model that performs no better than random guessing. So now, an AUC of 0.89 suggests that the model has a good discriminative ability. That means the model is good. So now the dotted line represents a no skew classifier. That's random guessing. And the closer the ROC curve is to the top left corner, the better the model. So this curve that you are seeing, the better it moves closer to this place here, you can see, then the better the performance, the better the model. But if this orange line moves closer to this line, then that means the model is not actually very good. But if this orange line moves below, this line here, that means no, that the model is useless. That's just it. So, but with this here, we see that the model is very okay. Now, for the precision recall curve using cross validation, so this curve plots precision on the y-axis against recall on the x-axis. Precision is the ratio of true positive to the total number of predicted positives. So while recall is the same as the TPR or sensitivity, so the curve shows the trade-off between precision and recall for different threshold values. So a perfect classifier would create a curve that goes to the top right corner, so a perfect classifier. So the top right corner. So the more this curve moves closer to this edge here and comes down here, then we can see that the model precision is that a perfect classifier. So we have a perfect classifier. So now the model precision starts to decrease as recalls increases. So which is a typical behavior. So the area under the precision curve can also be used as a measure of model performance, particularly in an imbalanced classification problem. So for an imbalanced data, then we can always make reference to precision recall curve using cross validation. Yes. So now for the confusion matrix, so we have this. We have the true label and we have the predicted label. So what does this mean? What does this mean? So you see here we have 0 to 1. Yeah, we have 0 to 0, 0 to 1. Yeah, in this case, we have 1 to 1. So the explanation is that the confusion matrix is a table used to describe the performance of a classification model. So each cell in the matrix shows the counts of true and false prediction. So the top left cell, which is 514, you see this, it indicates the number of true negative, mean model correctly predicted the negative class. So the
You
number of
can't see
times the
your screen,
model
Sam.
correctly predicted
We can't see
the
the
negative class.
screen, Sam.
Okay, this is it. Can you see my screen? So the number of time it predicted the
You,
true negative
we are seeing
is
it.
514. Is 514 times. So which is this? So and also the bottom right cell, which is 252, number of um, indicates the number of true positive, meaning the number of times the model correctly predicted the positive class. This is the number of times it predicted the positive class. So which is this? Yeah. And now, if we look at this, we have the top right cell, which is 35, indicates the false positive, where the model incorrectly predicted the positive class. So 35 times, so it did that 35 times, incorrectly predicted the positive class. And for the bottom left, so left cell, which is 90, indicates that it actually indicates the false negative. So where the model incorrectly predicted the negative class. So now with this, actually, with the fact that this value is higher here and is higher here, then it shows that the confusion matrix is telling us that okay, actually the model actually can predict the negative true negative 514 times correctly, and the true positive 252 times, but the true false negative 35 times, and the false positive um, that is 90 times. So that's what the confusion matrix is about. So now the confusion matrix provides a straightforward way to measure the model's accuracy, sensitivity, specificity, precision, and recall. So that's what confusion matrix is used for. So it's a particular metrics that we can use. So the ROC curve and the AUC values suggest that the model is good at distinguishing between the classes. So the precision recall curve is useful when dealing with imbalanced classes and also indicates decent model performance. The confusion matrix breaks down the correct and incorrect predictions, allowing for a more detailed understanding of the model's behavior. So this gives us the model behavior. So now, the summary is this: is that of the potential of different learning algorithms for selecting best fit based on data pattern. So the endeavor involved an intricate process of data preparation, standardization, and analysis using sophisticated machine learning algorithms So the data set encompasses a variety of attributes such as passenger ID, survive, P class name, and so on. So throughout the project, we harness the power of Python, particularly libraries like Pandas, scikit-learn, and Seaborn to conduct exploratory data analysis, visualize complex relationships, and build a predictive model using different machine learning algorithms. So the model's performance was evaluated using metrics like accuracy, precision, recall, and the ROC curve. So while the accuracy for the best machine learning algorithm stood at 86%, approximately for the voting classifier, and a standalone accuracy of 85.7%, both for feature selection and tune parameter, respectively, for the Gaussian process, which we talk. So in the model retraining, so indicating high predictive power. So the model exhibited a significant performance toward the majority class, highlighting the need to choose it above other algorithms, which is for the Gaussian process. Now, conclusion. Now, concluding it, we observe that the data visualization and machine learning provide profound insight into selecting best fits based on data pattern, facilitating informed choice for selecting a class of machine learning algorithm. So the voting classifier and Gaussian process algorithm, particularly Gaussian process, served as the project cornerstone for this training, offering a glimpse into the predictive capabilities of machine learning. However, the model performance revealed critical limitations in the aspect of exploring new features in data, using a predictive model to impute age rather than a simple group by operation, investing more time in parameter tuning and model optimization, prioritizing models and thus cutting more redundant features, exploring deep learning application. So, but it shows how important it is to carefully analyze data and have a data set with a good mix of different types of approach. So this helps build models that can select the best fit based data patterns. So now, recommendation. So based on findings and conclusions, several recommendations emerge. Firstly, addressing the class of imbalance present in the data set is paramount, as it likely skews the model's ability to predict minority class accurately. Techniques such as smooth synthetic minority over sampling technique or adjusting class weights within the model may prove beneficial. Secondly, feature engineering could be pivotal in uncovering more profound relationship within the data, potentially leading to better model performance in the aspect of exploring new features in the data. So using a predictive model to impute age rather than a simple global operation. So investing more time in parameter tuning and model optimization. So now, thirdly, experimenting with different algorithms such as example method or neural network could yield improvement in prediction accuracy. Lastly, before I stop, incorporating a broader set of features, possibly through feature extraction technique or integrating external data sources, may enhance the model's ability to encapsulate the model complexity of the data set. This step could significantly contribute to the development of a model more robust, accurate, and model ultimately enhancing the selection of best fit in data pattern. So with this, I'll put a stop to it. So I hope you have been able to get a little or a few from this explanation. So thank you very much.
Right, you're welcome. Any question from the house? Any question, please?
Yeah. Can I go ahead?
Yeah, go ahead,
Yes,
please.
sir.
Okay. Thank you very much for the presentation. Um, there's no time to ask plenty questions, so let me just say this. So what you discussed is classification problem. So
Yes.
yeah, in the case of a regression problem, so let's take for example where there is a data from experiment. So and you have several feature variables, that determine a target variable. So
Yes.
in that case, all variables will be important for
Let
the
let
target
us
variable.
let us reserve that one till I meet you in May. Between first week and second week in May, I'll meet you to revise this machine learning in detail again.
Okay, thank you.
All right. Any question, please? The class will soon end.